You remember when we were talking about the complexity of semantics, Dung's argumentation framework semantics. Some of them are pretty nasty, right? Some results are pretty difficult. Some of them are NP complete. Some of them are even more hard. So what we know and what we can do right now about those semantics. If you have any question, ask her, because she is one of the author of this beautiful summary of implementations and techniques for addressing the computation of semantics extensions of Dung's argumentation framework. And it is coming out, it will come out some point in the future, a chapter on the first handbook of formal argumentation, describing techniques and implementations as well. Once again, just wait for that. Either 1 day or 2 years. Now, there are people proposing procedures. Well, because I mean, your colleague, what your colleague did before, what was that? It was searching in a graph, searching for a suitable solution of the complete labeling problem, right? So you know some of them were pretty easy, like computing the part that is the grounded labelings, right? And then you have to make some guesses and see whether the result was still satisfying the conditions on the complete labeling, right? You can write an algorithm for doing that. You start from the unattacked one, and you go on as much as you can with the grounded. And then you start picking one of them as in, and you go deep into all the others argument until you search for all of them, you assign the labeling for all of them, and if you find yourself stuck, that you cannot actually go in that direction, you have to backtrack. So let's suppose that you assigned, by mistake, this in, and you want to assign this as in. You can't. Which means that you made a mistake somewhere. Which means that you have to backtrack until the last reasonable solutions, and then find out another possible assignment. And this is the idea behind a work coming out from people in Liverpool, Samarno Fall, Puldon, and Katie Atkinson. And it's basically using a set of labels that are a little more expressive than the in, out, and undecided. And that's been done for the reason of trying to minimize the number of backtrack of coming back. And the idea is basically you start from everything is blank, and then you try to assign something as must out, and then you keep going on addressing what are the neighbors of your assumptions, and whether that is satisfiable, then you go deep and you search for something else that is outside your neighborhood. There are approaches that instead are translating a Dung's argumentation framework in something else. They reduce the problem of computing a Dung's argumentation framework semantics extension into another problem we already know, is already known in literature, and perhaps there are already solvers for that problem. So one of them is translating a Dung's argumentation framework into a constraint satisfaction problem. And basically a constraint satisfaction problem is when you have a domain that is mapping, well, that is the result, that is where some variables can map to, your variables. And then you have your constraints. Can be of various nature. And the idea is to find an assignment of your variables in the domain that satisfies your constraint. As we saw before, complete labeling at the end of the day is a set of constraints, right? So though you can rewrite those constraints as the constraints in this CSP, and then you have your variables that might be whether an argument is inside the extension or not. And the domain is probably just the set of arguments. So basically, what you do is create a variable for each argument, and the domain can be either 0, 1, so the argument is either inside an extension or not. You describe the constraint in some way, like A1 and A2. It means that it is conflict free if A1 is 1 and A1 is 1 is not the case. So you can specify those type of constraints given a Dung's argumentation framework, and then you can just run a CSP-based solver. And the result would be, given this simple constraints, just a set of conflict-free sets. You can specify more complex constraints, and this is giving you other semantics extensions. But there are other ways there are other systems you can reduce your problem to. And I think I should leave Sarah the stage at this point, basically. So please don't be bad with me if I make some mistakes. But the idea is, you have your problem in Dung's argumentation frameworks to address some semantics. You know that ASP, answer set programming, is already powerful enough to address most, if not all, of the problems related to Dung's argumentation framework. So you write a logic program. And for instance, this is the program for computing the stable extensions. And what you have, for instance, if you have that an argument is in and attacks y, if the argument y is in and attacks an argument x, then you can just conclude that the other argument is out, basically. So it's not so hard to read this program. It's hard to write a good one. Trust me. You can actually read them. There are some elements that you might be better off using some external tools, like subset maximality using MetaASP, or using some other approaches coming out from recent work in ASP. But the core idea is you write a program to just compute the semantics extension for you using a logic program. The last slides are related to is still another reduction-based system. So basically, a set problem is when you have a CSP where you are constraining your domain very much. It's just Boolean variables, basically. And the constraints are just Boolean operations. But the idea behind is actually the same. Why I treated them separately, it will be evident in 10 minutes. But Wolfgang, Matti, Johannes, and Stefan proposed one of the first implementation and actually very efficient procedure for computing Dung's semantics extensions using a set-based reduction system. And the idea is, well, if an argument attacks another argument, you basically says that there is a conflict, so you cannot have all of them together, and then you can express elements like admissibility and other constraints out of it. And this is the idea behind a tool called SIGARTIX. It is extremely well designed and well implemented. And the idea is, once you have all of these elements here, you just run a set solver. It's giving you a solution of your variables, and basically is giving you what argument is in, what argument is out. So you define your CSP problem as a set problem where you have a variable for each argument, and this variable can be either true or false. If it is true, it means that that argument is inside the extension. If it is false, it's not in the extension, and the constraints are providing you the reasons why you should believe that one is inside or not. It's basically giving you the constraints given by the semantics itself. And this is using just one variable for argument, right? True or false. But we saw here that there are 3 levels, right? In, out, and undecided. Sometimes, if you're just computing the extensions, you just care about the in arguments, right? But sometimes you might want to look inside and see what are the undecided arguments, or there might be reasons for looking inside the undecided argument as well. And that is, some other authors, including me, proposed a slightly different encoding of that, which is actually implementing directly the request of constraints of the complete labelings. So you have that, well, if an argument is not an attack, then the argument should be in. But, and then you have that, in general, an argument is in if all its attackers are out. An argument is out if at least one attacker is in. And then you have the other condition for the undecided. So this is a Boolean proposition, constraint. You can just write this into a such problem, which is what we did. The fact is, you can have multiple, well, this is the result of your encoding, because you have just to use conjunct in normal form instead of general Boolean formula. But you can actually have different encodings, because if you have that is a total function, you can just say that you just specify the condition for in and out, and leave out the undecided, because if you cannot satisfy neither in nor out, it's automatically undecided, right? Or you can specify out and undecided, or unsurprisingly in and undecided. But also you can define only if something is in, therefore, so not if and only if, or clearly the other way around. And actually there are another couple of combinations more weird. Now, why this is important? It's not important from a theoretical point of view. All of them are giving you the same exact result. It's important from an implementation point of view. This is the result of an experimentation using those different encodings. So one is with all the conditions for in, out, and undecided. One just for in and out and undecided, in and undecided, and then therefore or the necessary condition. And this is a logarithmic scale. And you see that this condition C2 is always performing at the top. And then the others, given a rise on the number of arguments, is dropping quite considerably. You don't need to know this from a theoretical point of view. You have to know this if you want to implement something that has to scale up to a certain level. Because this was about computing preferred extensions. The skeptical acceptance of an argument for preferred extension is at the second level of polynomial hierarchy, which means that is NP over an NP. So you know that a SAT solver is giving you an ability to solve an NP problem. A SAT problem is an NP complete problem. But this is, you need another level of complexity on top of that. So if you just look at what you could do with a naive implementation, you might end up with a very exponential growth of computation. But you can actually address most of them, given the idea coming out from Wolfgang Dvorak and colleagues in Vienna of using a SAT solver as an NP oracle. You just translate something that is very hard, like computing the complete labelings, into something that somebody else can address, a SAT solver. The SAT solver we have right now are extremely performant. You'd be surprised of how good they perform. So you just leave the hard part to the SAT solver and try to come out with something clever for the other part. But the way you're addressing the SAT solver might make a huge difference. So it's not true that you just say, yes, the SAT solver is great, leave the SAT solver to do the hard work. Yes, but you should help it as much as you can. And this is a reason why choosing the right encoding for a right framework might be quite difficult. I want to highlight this paper because it came out AKR this year, but it's very neat and very, I really like this paper very much. And the idea is, instead of do the hard work and came out with a nice algorithm for addressing a second level of complexity, and etc., you can just use something we already know is expressive enough, like second order logic. And what they do is just write down, damn, I forgot a backslash. Here. It should be an and, not a logical and. You can just write down all the conditions you want in pure logical formula. Like conflict freeness, you want to have any arguments that is attacking each other and both of them in the extension. Admissibility, well, you first want, auxiliary definition, you want to define attack and defeat, like something that is related to attacks and having something in the extension. And you want to define fixed point, you can define fixed point definition, fixed point solution like using the auxiliary definition before, and having something that is inside only is in a fixed point of a function that is the original definition of Dungs. I don't want to address you with technical issues. The key point is logic is already powerful enough. Second order logic is already powerful enough for you to do all this kind of stuff. What they actually did, people in Finland, was to come out with a neat way to translate all those logical encodings into a series of calls to different SAT solvers. You don't have to care about them. They are already optimized. You just write the logical formula, which is a very easy way to translate what you already have in your definition, and then the hard part is already done by the SAT solver. Different from what I said before, that you should have the SAT solver, the way they actually encoded this problem into SAT problems is so well performing that is good on average. It's not the best one, but it's good enough for most of the applications. And the nice thing is, if you have something new, a new semantics, you want just to create a solver for that, instead of trying to figure out what is the best way to do, you can just write a formula. And then you already have the tool behind that for computing the results. And you already have a solver out of it for free, basically. And no, I'm not the author of this paper. I just advertised it for free. But what I wanted to highlight here is these are the results of the last competition, last year. And this is skeptical acceptance of arguments. So if you have complete, preferred, grounded, and stable, and what you can say is, well, this is a SAT-based system, this is a CSP-based system, this is a SAT-based system, this is a ASP system, and this is a direct implementation. SAT-based, 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 ASP-based, SAT-based, ISP-based, and I don't remember the others. For grounded, this one was using a unit propagation of a SAT-based system, and what? Direct implementation, SAT-based, SAT-based, ISP-based, SAT-based, SAT-based, CSP-based. I can go on over. But the idea is, if you are looking at preferred, for instance, SAT-based are always the best one in the competition. For the moment. And if you will come at my talk, you will see that it's not always the case right now already. So, in the competition, for the rules of the competition, the SAT-based were among the best. And thanks for highlighting this one. Always remember, the results of a competition is not an absolute result. It's very much dependent on what are the benchmarks, what are the rules, a lot of things. So do not assume that for you a SAT-based system will be the best one. I don't know what is your problem. I don't know how hard it would be to translate into SAT. I don't know whether that is good enough for you. Do not take, the takeaway message is not SAT is the best. The takeaway message is this is the state, this is a picture that we had from a competition. And from the competition, given those rules, ASP and SAT-based are always in the best positions for most of the problems. That's it. And I leave it here with this picture of, do you know who is it? In ECAI 2014, there's been an invited talk of Olga Hus, this gentleman, who came out with this sentence: we need to be smart. And what he was saying is we need to exploit machine learning as much as we can and leave the machine to do the hard work for us and try to focus on more interesting problems. And this will be the topic of the next lecture.